and welcome to today's daily Leetcode challenge. I'll be going through the solution, I'll be explaining my thought process, and then stick around for the end of the video. We'll compare the solution that I got with solutions of others in the database. With that, let's begin question 542, 0, 1 matrix. So given an m by n binary matrix, mat, return the distance from the nearest zero for each cell. The distance between two adjacent cells is 1. Okay, in my own words, we're given a matrix. It's not a square matrix, it's an m by n matrix that is binary, meaning that the content of it is either zeros or ones. Return the distance between the nearest zero for each cell. So each cell at the output is going to have a number in it representing a distance to the nearest zero. And so let's look at some examples. Example 1, we have a 1 surrounded by all zeros, and so the result should probably be also 1 surrounded by all zeros, because for this, the distance to the closest zero is itself, so as for this index, and so on, except for the first one, where the distance to the closest zero is actually 1. So to the top, to the left, to the right, and to the bottom. Another example shows a similar matrix, but the bottom row is also all ones. And it seems like the only change here would be that the zeros there are still there. The 1 in the middle is still there, but this one, bottom center, would probably be a 2, because the closest zero to it, and not including diagonals, would be either this 0 or this 0. And the constraints indicate that the values in the initial matrix are either 0 or 1. The size of m and n is pretty large, 10 to the power of 4. And yeah, okay. Well, let's think about the solution. So I propose that I propose that we have to do a search. Now, this search over the whole matrix should probably be at starting at any of the zeros and going through to the rest, like propagating through the rest of the matrix and seeing where it can update a value, or seeing where it can update a distance value to something that is less than what is originally there. So what I'm proposing is to have a dist matrix where each value represents distance to the closest zero, and basically we would also do some sort of search over the matrix that propagates through the whole matrix, and also updates values, updates dists as it traverses. Now, what I'm thinking for the kind of search that I would use, a BFS or breadth first search sounds very reasonable, because in a breadth first search, you are almost guaranteed that everything around you is going to be visited, or everything close to you is going to be visited prior to something that is, let's say, maybe 2 steps ahead be visited, because of the nature of the breadth first search. And so I'm gonna say BFS here, breadth first search over the matrix, and yeah, that's pretty much what I'm thinking now. During our BFS traversal, we also need to make constantly the decision of whether to update a specific value with a lesser distance or not. And so in order for that to happen, I'm thinking of pre-populating the matrix, the output matrix, with some extremely high number, maybe the maximum number, which in this case is just m times n. And what else? Yeah. So now to sum up what I've come up with, I'm going to implement a BFS algorithm that traverses this matrix. The BFS algorithm is going to start from every available 0, and there should at least be 1. There's at least 1 0 in the matrix. And this BFS is going to start at a specific or a possible 0, start at initially at 1 0, but it's also going to look at all the other zeros, and it's going to update values, update its neighbors to the best possible distance to the 0 where it started from. After we iterate through, or after we do BFS from all the zeros, we are essentially guaranteed to find the best distance for all of the elements in the matrix. And that's it. So with that, let's start the implementation. Let me quickly count first the length, the m and the n. N representing the number of rows, and m representing the number of columns. Let's also have a max value, which is just going to be m times n, or n times m. And I was sort of thinking about the output matrix that we're going to have, and we could have our own one. So we could create a new matrix that's going to serve as the output. But what I also noticed is that the input matrix, since it's a binary matrix, we could very easily just utilize that. What do I mean by that? Let's say that for I in length, or I in range n, which is going to over the rows, for j in range m, we're going to say that if the matrix of I and j is equal to 0, then we're going to leave the matrix value at 0 as is, but let me pass this for now. But else, we're going to actually update this value to be the max value. I'm updating this to be the max value partially because I want to make sure that, although I don't even need to update it. No, I do need to update it. I do need to update it to max value because in a scenario where the value 1 is in there and value 1 is less than the true value of this point, which is 2, if I was to write my algorithm that looks at the minimum for that value and the current of what is in that value, then 1 would be picked up rather than the true value, which is 2. So I'm actually going to update matrix values that are not set to 0 to the max value to kind of put it in the worst case scenario. But why I did this pass here is because I want to keep track of the positions of the starting points that I'm going to need. Starting. So what I mean by these starting points is, if you remember, I said that we're going to be using BFS, and BFS is usually implemented using a queue. So I'm going to have a queue. I'm gonna have a DQ. I'm gonna have a DQ because I'm gonna be appending to the right and popping from the left. I'm going to append to the end of it a tuple of ij indicating where my zeros are going to be. So now, just as a temporary step, let me print all the starting points that I've calculated. And I like to do these incremental steps to make sure that I'm doing everything correctly. But for the first test case, which is this one, I have a 0 at 0, 0, 0, 1, 0, 2, 1, 0, 1, 2, and then 2, 0, 2, 1, 2, 2. So I'm great here. Same goes for this. So now that we have a set of starting points, let's create our traversal algorithm. And a BFS traversal algorithm is usually implemented with a queue, as I mentioned before, but in this case, our queue is going to be, it's not just going to be like a binary tree, right? We're going to need to look up, left, bottom, right. And so I'm going to have not just 2 in a binary tree, but I'm going to have 4 places to go. So I'm going to have a move array, where I will hard code left, which would be something like, what is left? No, let's do top first. So top would be, I'm not moving a row, but I'm moving a negative column. Then I would have not moving a row, but moving a column down, so bottom. I'm going to have a move left, but not moving a row. And finally, I'm going to have a move right, but not moving the column. So this indicates, if I was to apply this tuple to my 0, 0 index, this would be moving me up 1. This would be moving me down 1. This wouldn't be moving me to the left. This would be moving me to the right. Awesome. And so now, pure BFS algorithm. While Q, so while my possible starting points are not empty, I'm going to say for row and column in let's call this position. Doesn't really sound good if I say, or no, move sounds good. For row and column, or let's call this dr, d column, so the difference in the movement, right? I'm going to say that row and column is equal to sorry, I'm thinking while Q, I have to say row and column is equal to Q pop left. So I've pop left the next position that I'm looking at. And for my moves, which is a difference in row, difference in column, I'm going to say that now my true values that I'm exploring, let's call, I'm so bad at naming the call, and this is going to be R and C. What are my moves now? Well, my moves are row plus dr and call plus dc. What this is doing is making sure that I'm at some point looking up, looking to the left, looking to the right, and looking at the bottom. And now for the final condition, which is going to be me figuring out if a position that I'm considering is actually worth exploring next. So if 0, so if I'm not outside of the bounds of, let's see, 0 row and less than n, which is the number of rows, and 0 column m, and let's see, and also that my matrix with my row and my column that I'm looking at is larger than the matrix point where I'm currently at, which is row and column plus 1. In that case, I would actually like to update my matrix row and column to be equal to this, because I've now found a place, a better distance. And I'm also going to say now q append, and I'm going to append this a new place for me to explore. So now that I've updated a new location with a better distance, it theoretically means that there's neighboring locations that should also be looked at. So this one is going to be updated with a row and a column as well. And let's see if this works. Hopefully, unknown network error, please try again. Hopefully Leetcode isn't down again. It has been down a couple of times before. And it seems like we've came up to the solution. Let's see if this works. Awesome. Great. Beats a good number of solutions, but there seems to be better ones available. Quickly, let me summarize what we're doing here. We're employing a BFS algorithm, breadth first search, to traverse the input matrix, starting from each 0. Now, purely visually, I see this as almost this like electricity sparking from each 0 and traversing each possible neighboring index and updating values, and also taking in those values and putting them into the next possible location to explore. So in the first breadth, we're going to explore basically all locations that start with 0. The next set is going to be explore all the ones, right, and so on. So the first traversal, and this is not very clear because Q is not a DQ doesn't have this property of like separation of points that we want to explore. But what a queue does is it enables us to append the worst or the next possible location to explore to the end, prioritizing things that have not yet been explored. And so initially, as you can see here, we've only populated the queue with indices that have a 0 value in it. However, in this portion, I'm guaranteed to only populate the next set of locations or the next set of points with ones. And that's because of this property that matrix RC is greater than matrix row and column plus 1. If yes, then update it and add that value to the next one. So we're guaranteed for the next set of things that are added to Q to just be added with points that are equal to 1. And then after all the points that are equal to 1 have been looked at, the next set of points starting with 2 are going to be looked at. This way, we're essentially guaranteeing that a point of exploration is never, or a point that has a non-zero value will inevitably get the best possible solution, because priority in this takes the lead. First it's zeros, then it's ones, then it's twos, and so on. Okay, with that out of the way, let's look at some better solutions, and hopefully we can get something out of them. Okay, this one is extremely short, update matrix, but let's just talk through what they're doing. They're getting they're getting the lengths, the number of rows and the number of columns, and then claiming that for I and row in enumerate matrix. And enumerating matrix, what would that even do? That would give you the index of the row and then the row itself. And then for J in cell, so now I'm looking at the index of the row and the index of the column and the cell. If cell, and cell I'm assuming is, because this is the first iteration, it's not going to be a 0 value. So if cell equaling to 1, I'm going to set the matrix I minus J, which will just be the top row. Oh, they're saying if I, meaning that if I is non-zero, right? If I, then set it to the top. I see. So this is just setting the top value and infinite if in the case where I happens to be the topmost row. This is setting the left, same logic but for the column, and then saying that matrix equals min top left. So this is updating the value that I'm looking at to a minimum of either the top or the left. And visually, I'm thinking this is going to be like, you're starting from, wow, so how does this work? They're starting from the on a row by cell basis, so they're prioritizing rows first, and at a specific row I'm going to look at each cell and I'm going to take the min value from the top and the left and get it equal to what my mat ij is equal to. And so you can see that after the first set of for loops, it's almost going to be that the value to the bottom right is calculated on the basis of what my top and my left are calculated to. And then you're reversing both. And then I'm assuming it has to do it back up, right? So what is reversed range M? What is reversed range M. Range M is just going to be, what is range M? Is the number of columns. So it's going to start from 0 to M, but it's reversed. So M to 0. So it's going to look at, so it's going to start at the bottommost row, and I'm guessing the rightmost column. And if cell, and what is this value? If cell, oh, you're getting cell equal to, and seeing that mat is equal to something that's not 1, you're going to calculate the bottom, the right, and then you're going to get the min to be the cell itself, the bottom, and the right. Okay. I purely visually understand what's happening. Imagine a square, and you're applying this almost like diagonal line to it, and you're scrubbing it across the square and making sure that each value that the line is about to scrub over is being calculated with a minimum of the top and the left. So I could definitely try to write this. I just don't understand how this works. How come? Yeah, I don't understand how this works. But this seems like a very, very unique solution, making it almost very specific to this certain problem. Nevertheless, it's the fastest one. So yeah, with regards to what the best is, it seems like the one that they were proposing is faster. Not a significant amount, but what's worse about that solution is that it's very specific to this unique problem, whereas the BFS approach is very standard. It seems, on an intuitive level, it seems like that is the best way to do it. So I would still recommend this, and with that, I think let's cut it here. Thanks for watching. Like and subscribe, and I will see you tomorrow. Bye.